The conservation of muskoxen has received some promising news, according to findings from a recently completed genome assembly of a muskox from Banks Island in the Canadian Arctic. The study, led by researchers C. Locke and Stephen W. Scherer from the Center for Applied Genomics/CGN, the Hospital for Sick Children, and the University of Toronto, marks the first reported chromosomal-level genome assembly of this iconic species. This groundbreaking work provides key insights into the genetic makeup of muskoxen, offering hope for their conservation. Muskoxen have faced significant population fluctuations over thousands of years, experiencing sharp reductions that have reduced their genetic diversity to concerning levels. In fact, muskoxen have one of the lowest levels of genetic variation recorded among mammals. Genetic diversity is critical for a species' ability to adapt to environmental changes, and low diversity can make populations more vulnerable to disease and other stresses. With the Arctic undergoing rapid warming and increasing disease outbreaks among muskoxen, there have been fears that the species' low genetic diversity might lead to compromised immune systems, further endangering their survival. In this challenging environment, the Inuit people have played a crucial role as the eyes on the ground, working in collaboration with scientists to monitor muskox health. A long-standing partnership exists between the Inuit and the University of Calgary's Faculty of Veterinary Medicine, under the leadership of Dr. Susan Cutts. This collaboration has helped detect and diagnose diseases affecting muskoxen. In recent years, this partnership has reported alarming findings, including outbreaks of disease and a sharp 74% decline in muskox populations in some areas. This is particularly troubling because, in the 1990s, the Central Arctic islands of Banks and Victoria were home to almost 70% of the world's muskoxen. However, the results of the genome assembly offer some optimistic news. Two important findings suggest that muskoxen may be more resilient to disease and environmental disruptions than previously thought. The first encouraging discovery is that the annotated genome revealed a full complement of known immune genes, with no signs of immune deficiencies. Particularly surprising was the finding that the major histocompatibility complex, MHC, a critical part of the immune system involved in pathogen recognition, was more genetically diverse than expected. This discovery suggests that the muskox's immune system may not be as compromised as initially feared, even though the overall genetic diversity of the species is low. In addition to this, researchers found that muskoxen from other Arctic islands showed similar diversity in their MHC genes. This indicates that the recent disease outbreaks and population declines may not be directly linked to a lack of genetic diversity or immune deficiencies in the muskox itself. On the other hand, the pathogens affecting muskoxen have shown adaptive capacity, with the recent emergence of multiple virulence genes in the Arctic clone of erysipelas, a serious bacterial disease. The identification of these virulence genes, together with the newly assembled muskox genome, provides a valuable resource for studying the pathophysiology of emerging diseases in the Arctic. Beyond immune system genes, the researchers also annotated genes associated with rapid evolution and positive selection. These genes are linked to adaptations to the Arctic's extreme environment, including those involved in brown fat metabolism, which helps animals survive in cold climates, and circadian rhythm regulation, which is important for coping with the Arctic's extreme light and dark cycles. Additionally, the researchers identified genes with potential socioeconomic benefits for Arctic communities, such as those associated with the production of kiviot, the soft wool-like fiber that lies beneath the muskox's dark guard hairs. Kiviot is highly prized for its fineness, similar to cashmere, and has a luxury market. The muskox has long been an emblematic species of the Canadian High Arctic, with its flowing dark hair and remarkable ability to withstand the harsh Arctic climate. Muskox ancestors first appeared around 12 million years ago, with muskoxen themselves emerging at least 1 million years ago. Throughout their history, muskox populations have risen and fallen in response to climate changes. Their range was at its peak some 30,000 years ago, spanning northern Russia, Europe, and North America. However, by about 6,000 years ago, they had disappeared from Europe, followed by their disappearance from Russia about 2,000 years ago, and finally from Alaska by the late 1800s. By the early 20th century, muskoxen were only found in Arctic Canada and eastern Greenland. While early human populations, including the Thule Inuit, certainly hunted muskoxen, human activity likely did not play a major role in their early population declines. However, in the 19th century, a growing demand for muskox hides, mainly exported to Europe, led to widespread hunting and a significant collapse in muskox populations. By the early 1900s, only a few scattered populations remained in the Canadian Arctic, and the species experienced another genetic bottleneck. Despite these challenges, muskoxen have shown a remarkable ability to recover. The small populations that survived in the early 20th century rebounded, and by the 1990s, muskoxen were expanding into areas where they had not been seen in living memory, even reaching the northern edges of the boreal forests. Muskoxen have also thrived in areas where they have been deliberately reintroduced, including Alaska, Russia, western Greenland, and northern Quebec. These animals have demonstrated an impressive ability to adapt to a wide range of climates and environments, from the tree-line to the high Arctic. However, muskox recovery is not always straightforward. In some areas, after decades of population growth, their recovery seems to plateau, while in other regions, such as the large Canadian Arctic islands, muskox populations are once again declining sharply. The newly completed genome assembly is a crucial first step toward understanding the complex patterns of regional muskox population changes and exploring the species' adaptive capacity. This research also challenges some of the assumptions about the impacts of low genetic diversity on muskox survival. Future studies will delve deeper into the role of genetic bottlenecks in purging harmful genes and examine the roles of non-coding genome regions and epigenetic variation. The annotated genome will also be an important tool for studying the connectivity between geographically isolated muskox populations and assessing how local adaptations might inform conservation efforts. Given the rapidly warming Arctic and the increasing stresses facing muskoxen, particularly during hot summers, there is an urgent need to understand their adaptive capacity and genetic resilience. The genome assembly provides a valuable resource for conservationists, helping to inform strategies that can protect this iconic species in the face of a changing climate.